Charles William Kern. After I graduated from Carnegie Institute of Technology, now known as Carnegie Mellon University in Pittsburgh, I had the opportunity to continue my education beyond the bachelor's degree, and that was achieved through the University of Minnesota, where I studied for 2 years more before transferring with my advisor to Harvard University, Department of Chemistry. I finished my education at Harvard, my graduate work. Following that, I accepted a postdoctoral fellow appointment at Columbia University in New York. It just turned out that both my graduate advisor and my postdoc advisor were awarded Nobel Prizes for their work. For that reason, I'm often asked questions about what it was like to work in those kind of laboratories where all hands were of the highest order. What drew me to this field was the periodic table. I thought chemistry was an easy topic because all the hard work had been done in the 1890s by Russian chemists. Also at that time, I was studying, there was great interest in applying the laws of physics to the periodic table and trying to understand structures and reactions of molecules, the chemical side, in a deeper way using the laws of physics. In doing that, I learned to use computers. And at Carnegie Tech in those days, they received one of the first university-based supercomputers. I use that term in quotation marks because it was a very large computer occupying about the space of the room we're talking in, from the floor to the ceiling, with all kinds of electronics. And in order to make the computer work, you had to do two things. One was plug it in, and the other was to write the programs and manufacture the data that was going into the computer as input, and of course understanding the results as it came out. And in those days we did not have rudimentary software, user-friendly software, and so all the instructions and the data had to be converted into zeros and ones. That was a language that the computers of those days understood. And that particular computer at Carnegie Tech was manufactured by IBM, International Business Machines, and eventually most universities developed very active scientific computing departments for all kinds of things, such as orbits of the moon around the Earth and so forth. I suppose the big break in my career was realizing that I liked the university environment. I had no great ambition. I didn't want to be professor of X, Y, or Z, or associated with a commercial company. My main ambition was to study and to learn and to be part of the intellectual establishment in the United States. So every step of the way involved transferring to a new university environment or studying with a different person in order to get an overview of a given field, such as the one I mentioned a few moments ago, quantum chemistry it's called. the application of computers, large-scale computers, to chemical problems. My family was not very enthusiastic about my studies, mostly because they thought it was time for me to get a job and to make money to support myself. But also, that turned out to be the time that the government, U.S. government, was beginning to hand out grants to people like me who wanted to do all kinds of research into various scientific subjects, including the interface between chemistry and physics. So in those days, that was translated into a major field of study, chemistry, and a minor field of study, physics. And that was the way the graduate programs were structured in those times. There were a variety of junctures where achievements were apparent, and most of them were reinforced by peers, such as the individuals I was studying with or fellow students who thought that the way I was solving problems was not only correct, but could lead to new results. That's a very general answer. And what was interesting about the way my mind worked was that one was led from one type of research to another by simply following the results as they appeared, either things that I had done or things that were going on around me. So it was very important for me to have good colleagues, interesting people who were doing significant work. And by being part of those collections of students or professionals, usually young professionals, I learned a lot about which problems were worth investigating. And so I would be attracted to those kinds of problems in my own work. Mathematics and physical sciences of the field of chemical physics. And applied mathematics was very underrepresented at many universities, most universities. And that was a whole field that we spent a lot of time and investments in trying to cultivate. Well, I mentioned in my biography that was published by Marquis that when I was at Battelle, first 10 years of my career, I began to have some opportunity to bring investigators together and work together on common problems. And that was a mode of operation that was highly successful and led to a number of key scientific papers and published on their own. And the experience at NSF was certainly quite informative about the way the government decided on projects and the openness with which they were always interested in finding a new and different idea and providing financial support toward achieving it. The CSNet being one of the major things that I was involved in. I was actually, the project for NSF was set up for 5 years, and I was in the project for 3 years, and I felt that I had done enough to achieve the objectives, and I wrote a report submitted to management to that effect. But after that, I was interested in going back to university myself as a professor of chemistry and working with students. And I knew a lot of folks at Ohio State University, and when the deanship came up for a reappointment, they urged me to apply, and I did. And so I was dean of the College of Mathematical and Computer Sciences at Ohio State, Physical Sciences, and following that assignment, I went to Northwestern University, where I was vice president for research and graduate studies at Northwestern. In the literature from Ohio State, I'd frequently find the phrase excellence. Everything we're going to do is excellent. But the real question is, what does that mean? How do you measure excellence? Who decides? And what implications does it have for the future? And it happened that the College of Mathematical and Physical Sciences at Ohio State was very rich in talent. I knew that, and everyone else did too. And so they were, as a group, quite successful in developing their reputations, the reputations of their departments. And in the process, we had the opportunity to compete with other colleges across the campus of a very large university, 50,000 students. So that aspect of scientific life was a realization of how it can be used to help define excellence of programs. I found to be quite interesting. Well, certainly personal inspirations included the peers that I was associated with and worked with over the years in various fields, including chemistry, physics, mathematics, and computer sciences. There was also a management component that became part of my style and important, and that was to be open and honest and make a real attempt to connect with investigators and what they were thinking and trying to achieve, and helping to find what steps to be taking in order to arrive at answers that they would find achievable. The fields that I was interested in were not the humanities. They still struggle for funding, but the scientific community, by and large, was well funded by the government and by industry, for that matter, throughout America. One of the legacies that has been achieved in the last years has been through the Marquis programs. And I'm very pleased to be part of that. And in a way, the recognition coming from them is particularly valuable because I had nothing to do in the choices they made. These were independent committees that went through the bios available to them throughout the country and chosen independently of my own personal input. I would say the single most important advice I would have for a young person today would be to start at university and stick with it. And as long as you feel that you're learning new things and making a contribution to societal needs, whether it be the environment or whether it be some other aspect, which could be something very esoteric, such as building telescopes in the Andes, which is what young people do these days in astronomy. One has to realize that when you look up at the night sky, There are millions and billions of objects up there, and anyone has to respect that and to ask the big question: how do we get here, and where are we going next? And I think that is very exciting and leads to many, many unanswered questions that are part of the future. And if the student should find that exciting, that's a great field of study because there are so many unanswered questions. If I had to summarize my life's work, it would be the pursuit of using high-end computer technology for all kinds of applications of physics. Laws of physics to chemistry are wide open, even today, and that's because the equations are very difficult to solve, even with very fast computers and more or less limitless amounts of memory. It's a hard problem, and certainly new techniques are to be discovered that would assist with that process. Well, I'd like to be remembered based on the body of work that I've been associated with and the people I've had the opportunity and pleasure to work with, my colleagues in fact. I never imagined that I would be at the point where I'd even have to answer this question. But that's about the best answer. Not so much the things, but the people that I had the honor of working with.